Okay, today's lecture is about our gravitational field, and so I want you guys to imagine that we have that we're on the ground. Here's our flat surface, and we have a crate. Yes, of course we have a crate because crates are our friends, and all I want for Christmas is a crate because I already got my new iPhone for Christmas. Well, there's our crate, and on this crate we have some forces with a force here, and we've got the force of gravity acting on the crate, and the force of gravity here Okay, so here we have a gravitational field. That's what we're working on today. So here's a surface, and on our surface we have, of course, a crate, because all a physicist wants for Christmas is, a crate and a new iPhone. Well, I got my new iPhone, so here's our crate. And this crate has forces on it. It's got the force of gravity acts upon this crate. There are other forces acting on the crate, but in particular we're concerned about gravity today. And this is close to the surface of the Earth, and so, in fact, even if we have some other object that's out here, okay, and this object will also have a force acting on it, okay, and the force acting on this is Fg is equal to the mass times its acceleration. Well, there's another way of looking at this, and we can determine what this acceleration is. Okay, and we've come to call this acceleration the acceleration under the influence of gravity. We have come near the surface of the Earth. We have come to call g, and with the vector pointing towards the center of the Earth. And this equals our force of gravity divided by the mass of the object that's getting accelerated. Okay, and so this also answers another question for us, and this is the question: how much pull per kilogram is acting on our object's mass, okay, or acting on any object's mass when we're close to the surface of the Earth. Okay, and that means that we're going to have that our g is actually equal to a different kind of term, and our g is equal to the number of newtons per kilogram that's acting on our crate. And notice our crate is not accelerating, okay, right now, because it's got it's sitting on the planet, but it always has. But at this moment, it still has this downward force acting on it, and so it is within this field that even there's still this centripetal force acting on it, and so we can extend this, but if we lift this crate to a place that's further away from the center of the planet, okay, we'll go with that. And it's a mediocre circle. Okay, so here's our mass of our planet, and let's say we have a mass here, okay, and we have a different mass out here, and then there's a different mass that's way over here, okay, and then we have another mass that is way over here, okay, and all of these are experiencing a force towards the center of our planet, and all of them are under what's called the effect of the gravitational field. All of them are in the gravitational field of the planet. And so how many newtons of force per unit kilogram are each of these guys experiencing? Well, what the difference is that they all have different radii from their source mass. And so g, for all of these, we can't just call it 9.8 meters per second anymore. We have to do something else with it. Well, the value of our g, it is still, however, the force of gravity acting on the object divided by the mass. All right, and what does this equal? Well, our force of gravity, according to Newton is now our gravitational constant times the mass of our big object times the mass of our little object, okay, divided by r squared, because that's our force, and this is in the negative r hat direction, remember, which means it's towards the center of the force on this is acting towards the center of that. Okay, and here's our m, so we're going to divide this whole thing by our little m, the mass of the accelerating object, and then all of a sudden that goes away and that goes away, and we are left with a g that is equal to big G, big M over r squared, the negative r hat direction, and this is in units of newtons per kilogram, and this is our our field. This is the acceleration due to gravity when you are around this planet. And now if you notice that these if you imagine the line, if you start building lines, putting mass in regular places as we move out around from the planet, that these lines, if we draw them straight to the surface, these lines, if we extend them out to infinity, that they would start getting further apart as our radius from m increases. Okay, so as r increases, as we move away from the planet, the lines get further apart, and that means that we have a weaker gravitational field. So as r increases, the gravitational field decreases as we move further away from the planet. And that's the basic idea behind gravitational field. And I know it's a really short little lecture right there, but that is the idea behind the gravitational field. This is the first of three forces that we're going to see. The other two are electrical field, okay, or electric field, and the other is magnetic field. Okay, so another way to think of this is if you draw a whole bunch of, let's say you draw 100 lines out from the center of, or degrees. You have 360 lines coming out of our mass right here, and as those 360 lines get bigger and bigger, you know, and so they line up with my little compass right here. So here's the center, and here's, now this is what I need to be doing to draw my circle. Let's draw this just for the heck of it. Now there's a circle. Okay. But if we start drawing each one of these little teeny tiny, ticks around the edge of my protractor here is a line shooting out of the M. Well, what happens as we move further and further away is that those lines start getting further apart, and as you go through, and there's actually a term we're going to see eventually. It's called flux, and it is the number of field lines that pass through a unit of area, and it's a concept by David Faraday that came up with flux, and it's very difficult to specifically quantify. But you can determine flux through the rate at which it changes, but you cannot determine any particular amount. It's kind of like our physical, our potential energy when we're establishing something from infinitely far. Well, actually, that's going to be the next lecture. So we'll talk about that next lecture, and then we'll talk. Hopefully, we'll talk a little bit about flux at that point.